Hi, welcome to this video. I'm Mohammad Akram. I'm gonna explain my image steganography project which I've done using advanced C concepts. So let's quickly move on to it. So before moving on to it, we need to know what is actually steganography is. Steganography is nothing much. It's just a process of hiding data inside file. The file may be a image file, it may be an audio file, it may be a video file. So we are just going to encrypt secret data inside a file, and we're going to decrypt on the other side. So in real time, where it is used, we could see these applications in military purposes, in digital transformation, IT sectors, where for a real time example, you can take it WhatsApp. So it's end-to-end encrypted. The message we send to the other person, it's completely encoded from one end and it's decoded at the other end. So WhatsApp is a good example for steganography, where the data gets hidden and decoded at the other end. So when we move on to the next, why it is used, simply we can say that it's hiding a credential, some highly confidential data which needed to be known by certain person alone. And it may use to detect data forgery, wherein if a data is theft, we can prevent it, and for message passing. So as I said earlier, where it is used used mainly in military, where confidentiality plays a major role, and in intelligence agencies, and in elections, internet banking, medical imaging, and so on. So how steganography is implemented? We could implement it using physical method, prints, paints, puzzles, digital. So how we are gonna do here? It's we're gonna encode the data inside a image file and decode it. So actually, it's image steganography what we are going to do it here. So I'll show the demo at the end of this video. This is just though there are different possible methods available, we would go with digital steganography. Actually, we are going with the digital steganography because we are using a image file. And digital method, the message is concealed within the lowest bits of image or sound files. So actually, what we are going to do, there are two parts of data in bits, LSB and MSB. We gonna encode the data only in the LSB of the files. We are not going to change anything in the MSB side. So I'll explain why it is in the later part. And we're gonna take what type of image file. There are a lot of files like JPG, JPEG, PNG, but we're gonna use a BMP header file. It's also a kind of a image file. Let's say why we are using BMP file also. So why LSB file, not an MSB file? So the name signifies that it is a least significant bit. So changes made to that bit will not affect the code or data in a drastic way. I can say this is a binary value of 0, and I'm going to replace this as 1, the LSB bit. So the actual value is decimal value of this 8 bits are 0. The actual value of this is 0, 1. Consider me changing the MSB of this bit as 1. So actually it is 1208. So we can see a drastic range difference between what happens if we change a bit in LSB and what happens if we change a bit in MSB. So modifying MSB changes the magnitude of the number to double, hence called as more significant. So any changes made to the MSB may affect the file or the program or a code. So we are going with LSP encoding and decoding part. So we are taking an image. Actually, what we are taking is an image steganography, and we are taking an image for our encoding and decoding part. What is an image? It's collection of pixels or an elements which is called as pixels, and they are grouped as row and columns with a fixed number of size. Next, so pixel is and can be said as a smallest addressable element in all points addressable display device. So it is the smallest controllable element of a picture represented on the screen. And each pixel is a sample of an original image. More samples typically provide more accurate representations of the original. Basically, the image is formed of a RGB data. So it consists of red, green, blue, and the other colors are cyan, magenta, yellow, and black. So this is just the two ways where an image. When modifying this RGB data, we could get any colored image. So here we can see this is the format of an image, and this is RGB. So if you change the values of red, green, blue at any instance, the color would be changed. So we could obtain any color by changing the values of RGB. And this is a standard way of getting a desired color. And you might get a question that why we using a BMP file? It's naturally an uncompressed file. Therefore, we could get more space to hide our data, and this is lossless. And it is its simple structure and wide acceptance in Windows programs gives an added advantage of using BMP file. So what does we'll see the frame format of the BMP. So the BMP would have first 54 bytes header. Continued by from the 55th byte, it will have the RGB data, as I said earlier, the red, green, blue pixels. So the 54 bytes header, we're not gonna. It's a standard header. We could not change anything. We just copy the whole headers. Complete 54 bytes header we need to copy while we are getting the image. And in the RGB data, only we gonna from the 55th byte, we're gonna encode our data, the secret message from a text file. We're gonna add it to the RGB data, and it's EOF is the end of the file. When it reaches, our file limit has been reached. So what these 54 bytes header would contain? It will have image magic signature in the sense it may have the image name, file size in bytes, and these are reserved bits, file offset to raise the data. And here this 14 bytes are reserved for only header. In this 54 bytes, only 14 bytes are used for header. The rest of the bytes are used for info header, and it contains these many datas. So we're not gonna change anything on this header and info header part. We'll just copy all those headers into our file. And the next one is an image format. This is how this is the replica of how the changes made to the RGB data affects the color. This is just a table. And next, as I said, why we are doing LSB modification rather than MSB, because you can see this is a red block. It's a red image, and this is the data, pixel data of the image. And you can see if I change any if I change the MSB part, you can see the color difference. There it is a bright red, and here it is a brown shaded. So clearly it shows how the changes in the MSB side reflects in the color part. So Actually, we are encoding an image, encoding our secret data inside an image, and we are gonna send it. If the color gets changed, so actually the end receiver would know that something has been changed. So there is no use in hiding our data, as the color would reveal everything. So we need to change only the LSB part, such that the color difference will not be much brighter. So I will show it on the other side. So the summary of the project is the project expects us to encode a message such a way that the quality of the image doesn't change much. So from the previous analysis, we can do encoding of bits from the message in the LSB of the RGB data. So we are gonna encode only our data in the RGB part, not in the header part. So the complete 54 bytes, we need to encode it from our source file. So this is the input we are going to give through command line. So first we will give we'll get an output file, and we need to describe whether we're gonna encode or decode. So this is the variables we use for encoding and decoding. For encoding, we will give a source BMP file, which image we have taken, and we're gonna give a secret file.txt, the secret file which has the secret message for us. So decoding, and we're gonna give -d, and we are gonna pass the BMP file which we got from here, from the encoding part, and the output file. It's optional. So I'll run the demo at the end of the video. So this is actually what happens when you do the encoding part. These are the messages or validation. You need to do internal validations for each and everything. And this is where you can see this is the original file and this is the encoded file. So you can see no changes. It has the encoded part, but it has very minimal changes. So we can't able to detect whether it is we have a secret data or not. So actually this is our output. This should be our output, and this is the decoding part. And we need to validate for decoding also. All the procedures are same, and we can get the cat secret.txt. What we have done it is. Next is we will take. This is the error handling part. If you have any error in the encoding or decoding part, it should be validated and it should be displayed. So this is encoding part. What happens? So I'll say before how encoding is going to be done here. Things we are going to encode in our data. Code in the image file. First is a magic string. So I'll explain what is a magic string. Actually, the magic string what I am using here is this one, hash star. So this is just a 2 character. So I had said first 54 bytes are headers and info headers. We are not gonna change anything in the first 54 bytes. In the from 54 byte, we encode starting from magic string. So what this magic string is used, why we are using this magic string is, say if I need to share encoded data with a person name called X, and I'm sending 5 files, including only one in those 5 files, only one file is has the encoded data, the other 4 doesn't have. So if the person X receives all those 5 files, he doesn't know which file is encoded at the first instance. So how he gonna know it? By decoding it. So I'm gonna add this magic string as my first uh, magic string as my first instance in encoding. So from 55th byte, this magic string would be present. So when the person X while he is decoding, when he catches up in 55 byte with a magic string, it will be easy for him to know that that if the magic string is present, you would know that that particular file is encoded or not. So it allows him to minimize the time for decoding. He doesn't want to decode all the 5 files. If a magic string is present in the 55th byte, he can encode only that file instead of going for in decoding all the files. Say it is 5 files, it's okay. When you send a file of 1,000 or more than that, this magic string would be very useful in time in making the time lesser. So this magic string will have characters. These 2 characters will be present. So I'm gonna we'll take this hash. This hash has unique. This ASCII value of this hash is 0 to 3. So when you take this as a binary value, you will get 0 0 0 0 1 0 0 0 1 1. This is the actual ASCII value of this hash. So we need to encode these 8 bits into the RGB data starting from 55th byte. So I'm gonna take so for example, you will take the value. My first value of my RGB data 55th bit is 0 1. So its value is 0 0 0 0. So in this, I'm gonna take this 0 and encode it in this LSB part. So what this value will be we will getting is 0 0 0 0 0 1. So 0. This is the actual value we will get after encoding. And for the next bit, this is for first, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. So for the first byte, I have encoded the data. First bit I have encoded. For the next, I will save. This is for the second bit, second 0. The same, if I have value as 0 2 and this value is 1, and I'm going to encode this 0 here. So my actual value will be after encode is the same, or else I take this 3, you'll have 1. So after encoding, so the range doesn't change too much. When you it was previously 3 and now it is 2, and it was previously 1 and now it is 0. So the range doesn't actually change much. This is what called LSB encoding. And the other important thing what we need to see here is, for 1 bit of data need to be encoded, you need 1 byte of data. So simple words, 1 bit requires 1 byte of data. So here, how many bits are there? It's typically 8 bits. So you need 8 byte of data for encoding this single character hash. It requires 8 byte of data. So for 1 character it is 8 bytes, mean 2 characters I'm going to encode. So my magic string requires 16 bits of data in bytes of data needed to be encoded. So the first part is magic string. So we need 16 bytes of data to be encoded for the magic string. So next thing we'll take the next part. So I said there would be a secret file, secret file.txt. This secret file will have my secret message. Say for example, my password is 1 2 3 4 5. So this is my secret password. This secret message need to be this is the secret message I'm gonna encode in my image, and this file contains that message. So what I'm gonna do is, in the second part, I need to encode the secret file size extension. So size of this .txt. So it's basically an integer. So I need 4 bytes. It is 4. So I'm gonna encode my .txt. The size of this .txt. So it has 4 characters. So you require 4 bytes of data. 4 bytes of data. Third thing I'm gonna encode is secret file extension. Secret file extension. This is actually a file size, and this is the extension. The extension is this .txt. These characters I'm gonna encode. First, I'm gonna encode this file extension. That is 4 bytes. It's actually an integer. So here it is a 4 character. We are gonna get. Actually, we're gonna take .txt. So we're gonna encode this .txt, which may require 4 byte. The next thing what I'm going to encode is secret file size. So I'm gonna encode this secret file size. Would have some size. So I'm gonna take that size. How much it is? So that may, for example, I should take it as 20 bytes. Next thing is secret data. I'm gonna take the size of this secret data in characters. So I'll take again 20 bytes. So totally you may require 16 plus this 4. So for one, I said earlier, for 1 byte you need 8 bits. So multiply this 4 by 8. So you may get 32. And for other, again, you this 4 bytes you need another 32 bits, 32 bytes. Similarly, for 20 characters, you may need this is actually an integer value. You're gonna take it as integer. So you need require around 32 again. When you look around this secret data, this character, so you may require 20 into 8 each bytes. So you may require 160 for this. So you may require 20 into 8, 160 bytes of data. So this much amount of data you need to encode all these things. So before starting your encoding part, you need to validate. There are a lot of validations. You should check whether the extension is a txt extension. You need to check whether my image file is a .bmp file. That file is present in the directory or not. So there are a lot of validations you need to undergo. And here you need to check whether your image has the capacity to encode these many bytes. If it doesn't have, you need to return a value that the space doesn't fit here. So this is actually the encoding part. You go through all these things. So I'll show the steps of flowchart of this. So encoding, you will start. You will check for read the command line whether it is encoding or not. If yes, you will check whether it is a file. Check whether the image is a BMP or not. So you will concurrently print the error message if it doesn't have. So followed by it, you will search for secret file is provided or not. Calculate the secret file size. Then will the secret message fit? You need to validate those. And is the file secret file empty? You need to check whether my secret file.txt is empty or not. So if it is empty, there is no use of encoding because there is no data to encode. So you need to return my error message. Actually, this no, yes, all these are validation part. I will show all those in a demo. Then create a file with provided name. It's all optional in your code. You can give the file name during runtime in the command line, or you can give a default. The programmer I have given in my case I have given a default name for the file. So this is happened. Next, this option -p provided. Set default magic string signature. Encode default magic string signature. So we are encoding a magic string, and this string use for magic string empty. And you need to check whether my magic string it's just as you define it as a macro, and you calculate the new size of for encoding. Will the secret message will fit? Encode magic string size, encode magic string, then error message. So all these are validation and verification parts. So finally, you will do encode input file extension, encode secret message, copy, and another important thing I forgot to say. This thing, all this data, you have some remaining data in your existing image. So you need to copy all those remaining RGB data also, because when you stop at this point, what about the image will have extra RGB data which may produce the colors. So if you stop at this end, your image will be different from what you expect. So you need to, after this, you need to encode to encode all the remaining data from the image till the end of file. So then only you will get the perfect image, or else the color would change. Next is decoding part. So the same, what the vice versa or what you did in encoding, you need to do the same things every. You should check whether the -d is passed, the check file is BMP or not. Is output file name provided? If yes, create a file with provided name, or else create a file with default name. So if you want to give a name, it checks the command name whether output file name is given or not. So it will check. If it is yes, it will create with the name what you provide in the command line, or else it will create a file with default name. And here start decryption. Stop. This is thing. So actually, this is encoding and decoding are a very important part of this project. So I'll show the demo of how it works. Actually, when I see it, so you can see already I have compiled program and I have two BMP files. So this is my source file and this default stego.bmp is my output file. So first I will run all the files. I didn't get any error, so I'll follow go on with c.out. I'll give my beautiful.bmp and secret.text. Okay, I didn't give my option whether I'm encoding or decoding, so I give. So this is the validation part. You will get encoding operation chosen, output file not mentioned, creating default stego.mbmp. So default stego.dbmp is my default name. So I'm opening the beautiful.bmp, open secret.text, open default stego.dmp. I'm printing messages. Encoding process starter. From this, encoding is starting. Check for BMP capacity to handle secret.text. So, as I said earlier, how much amount of data you need to, how many bytes you need, it should be available in your image file. So it will return found okay, copying image header. So starting, you should start with your image header. You copy all those 54 headers first, and then you start with your magic string signature, then your secret.file extension size, then secret.file extension, secret.file size, and data. You copy, I said, once you're done with this, you need to copy all the remaining data of the image file, and it shows encoding done successfully. So I'm going to do with my decoding part. Here I want to give decoding stego.default. So decoding part is also done perfectly. Opening required files, opening default.bmp, decoding magic string signature, the secret file extension site, open all required files, secret file size, secret file data, all is done perfectly. So I'll show both the output of the images. So this is AOG. So actually I'm in my skeleton is not required, so I'm already in my so this is my beautiful.bmp and this is default Steganography. So actually it has encoded data, but you can see no changes here. There are minimal changes, actually no changes. Both the images look similar. So this is our project. This shows our project is successful, and we can say that secret file dot. My password is Akram. So this is a file.txt is the default name I have given in my program. So we can see, I'll show that cat secret.txt. So my password is Akram. The secret.txt is the actual text file which has my data to be encoded. So this is my output file which is come after decoding. So both are same. So my encoding and decoding part has been successful and the secret message has been found. And there is no changes in the both the image files. You can, as I shown, there is no much. Actually, there is no changes. So this is what the all my project is. All the project was about. So I would in this session. Thank you all.